Swayam Prabha. Digital India. Educated India.
So, we have now been able to write these governing equations in this form, matrix form. So, I am rewriting this equation, sorry, this will be plus. So, this is free vibration multi-degree of freedom governing equation of motion. This is basically your response vector, which is q1, q2 corresponding to each of the degrees of freedom, q1t, q2t up to qn t, which is n cross 1 vector. Okay, and as we discussed, this is mass matrix is n cross n for an n degree of freedom system. The vector of accelerations are going to be n cross 1, all of them will be n cross 1, and then these are the square matrices n cross n. All right. Now, if you recall, we discussed in a 2 degree of freedom system, general vibration response is contributed by its corresponding the contribution to the vibratory response at each degree of freedom will be contributed by all its modes. Okay. So, what I can write here is that this x1, the response of the first mass, is going to be written as some arbitrary constant a1. You remember that we wrote this as cos pt or p1t minus phi 1 for a 2 degree of freedom system, and the contribution from the second mode, which is b1 cos p2t minus phi 2. And on similar lines, the mass 2 moves and its general vibratory response was given by a2 cos p1t. Again, the mass 2 also moves with a contribution coming from both the natural modes. So, p2 is the natural frequency in the second mode, p1 is the natural frequency in the first mode. You remember that a1 b1, a2 b2, phi 1 phi 2, these are all the arbitrary, these are all the constants which needs to be found from the using the initial conditions. But we also know that if the contribution comes from p1 or the first mode, the amplitudes of the first and second mass maintain some relationship, right, and that relationship is nothing but your mode shape. So, a1 by a2 by a1 was xr1, we defined this as the mode shape, and the b2 by b1 was xr2. Okay. So, if we now see this in a general one specific case of 2 mass system where the degree of freedom were 2, and then their numeric values were such that the mode shape was 1 1, then which actually means that a2 by a1 was 1 for p1 mode, and then the b2 upon b1 for the second natural frequency was minus 1. So, this mode shape was 1 minus 1. Why? Because b2 was equal to minus of b1. So, if b1 is 1, then b2 is minus 1. That's how it it happens. So, this 1 is nothing but your XR1 and this minus 1 is your XR2. Okay, that is what changes this x2 equation now. X2 equation will be written as A1 times XR1 cos P1t minus phi 1 plus, sorry, so I can write that as B1 XR2 cos P2t minus phi 2. Now, I can use these two equations x1t x2t equals to A1 and I can use this 1 and XR1 as the mode shape, first mode multiplied by A1 as a constant, and then that basically is your first column. Okay, that basically is your first column here, and the second column will be B1 1 and XR2, and I can use these harmonic time functions here. Now, you all know that if 1 XR1 is the first mode or a mode shape, then any constant multiplied by that is also a mode shape. Okay. So, what I am going to do is I will write this QT or the response of a multi-degree of freedom system. The way I can write this as a matrix which contains individual mode shapes like x1, x2 and so on, multiplied by cos p1t, cos, just ignoring the phi which can be accounted for later, but it essentially is a matrix containing all the mode shapes of an n degree of freedom system multiplied by the harmonic time functions. So, this in a similar line I can write this QT as a set of modal vectors. If I consider this to be n degree of freedom, then u1 u2 up to un would be these mode shapes or vector containing the relative displacement amplitudes of each degree of freedom, and then multiplied by what I will use here is a coordinate which I call as a principal coordinate or a normal coordinate, okay, eta t, which are nothing but these harmonic time functions. Now, this equation is a very powerful equation which basically defines what is known as modal analysis, wherein the physical coordinate is written in terms of principal coordinate, and this matrix contain all the modal parameters. Now, modal parameters, why? Because that matrix has the elements which are basically the mode shapes of this multi degree of freedom system. And why are we doing this? Please follow this process with patience. You will definitely realize later the power of using this transformation and how the solution process becomes so convenient, computationally convenient for solving many degrees of freedom system. Okay. Now, if we look at the governing equation of motion which I have written here, I have shown in some of the previous slides that your mass times, so this is p squared m into capital X was shown to be k times x, was it not? One of the uh, let us say ith natural frequency squared times mass matrix times the mode shape, which is maybe ith mode shape, was shown to be this way. Okay, this was the equation that we discussed the other day, right? Now, these mode shapes follow a property called as orthogonality. Okay, and we are basically going to discuss how this orthogonality property of the mode shapes can be made use of in the convenient and computationally efficient solution process. So, based on the equation that we had solved here and got this kind of an expression that we obtained, p squared m into x is equal to k into x. We will start from this particular equation where capital X is one of the mode shape or a modal vector, and p represent that particular natural frequency. Okay. So, I will rewrite this as k times, since we have been using u as these modal vectors, I shall now start using this u and I will use a subscript r to represent the rth mode shape, is equal to the natural frequency will be rth natural frequency. So, p r square times m into u r. Okay. This is what the same equation I have written slightly in a different form. Now, what I do is I will pre-multiply the entire equation by another mode shape or a vector representing sth mode shape. So, I will multiply the mode shape sth mode shape vector to this equation, and that gives me this equation. Okay. Now, the way I have got this equation, I can also get the equation when I consider the sth mode. So, if I am considering the sth mode, so when I consider the rth mode, I get this particular equation. If I use sth mode, I can write the equation to be us equal to ps square m times us, isn't it? Now, if I pre-multiply this equation by ur transpose, then the way I have got this equation number 1, I get equation number 2, which I am going to write it this way. Now, soon you will realize what are we up to. Just hold on for a while now, because it looks little weird why we are doing all of this. That is going to open up interesting things shortly. Okay. Now, as long as your matrices are symmetric, it is possible to show that these mode shapes being orthogonal, us transpose m ur is equal to UR transpose M US. This you can try on any sample example containing mass matrix or stiffness matrix. So, it is quite straightforward to show that this is true for mass and stiffness matrices. So, they being symmetry. So, UR or US transpose similarly for K matrix will also be the same way. So, you have UR is equal to UR transpose K into US. Okay. Now, we make use of this in rewriting these two equations now. So, what we are going to write here is I am going to write this equation as UR transpose K US is equal to PR square. So, I am writing this equation by invoking that relation that I have written here. Okay. So, this is one written or maybe I will write this as equation number 3, which I get by substituting this relationship in the equation number 1. Now, I will subtract 3 from 2. If I subtract equation 3 from 1, what I get? I get 0 here on the left hand side. On the right hand side, I get UR transpose M into US in bracket PS square minus PR square. Okay. Now, what does that mean? That if if R is equal to S, which means that I am talking of the same mode. Okay. When R is equal to S, PS and PR will be identical. They mean the same natural frequency. Numerically, that will mean that the bracket is 0. Okay. So, when R is equal to S, I can write that is not equal to 0, because this bracket is 0. And I can say that this is not equal to 0, but I can write that to be a quantity called MR. Okay. Now, what is MR? It is called generalized mass Rth mode generalized mass. Okay. If R is not equal to 0, if R is not equal to S, then for this equation to be true, what would it mean? UR transpose M US has to be equal to 0. Okay. And using the same in these equations, you can easily show. So, what you have shown is this. You can also show, just try it out yourself here in this equation number 3, that UR transpose K US is not equal to 0, but is equal to KR if R is equal to S, and is equal to 0 if R is not equal to S. Okay. So, these are basically the mathematical equations representing the orthogonality of the mode shapes with mass and stiffness matrices. They result into uh, these interesting outcome where Kr here is called as the generalized stiffness. Okay. Kr is called as the generalized stiffness in the Rth mode, similar to Mr, which is the generalized mass in the Rth mode. Now, hold on for a while, you would wonder as to how this is going to be of any use to us, in what way this is going to be of use, and trust me that sooner you will realize the potential and the utility of all these relationships that we have got here. All right. Now, if we go back to the equation, matrix equation, I am for the time being ignoring the damping matrix here. Okay. Now, the previous case where the orthogonality of mode shapes were discussed, what we got is the UR M into US. UR and US are basically Rth mode vector representing the Rth mode shape or Sth mode shape. What we discussed was that this turns out to be Mr for R is equal to S, okay, and this is equal to 0 when R is not equal to S. So, what we can do is these mode shapes can now be normalized. So, I am basically going to normalize the mode shapes by writing U tilde R equal to 1 by square root of Mr times UR. Again, this is done with being done with a specific purpose, and you will realize that shortly. So, I am basically the way we can get 1.05, 2.31 and 0.05, this kind of a mode shape you can get. What you can do is to get it is standard practice to normalize this with respect to the displacement of 1 of the degree of freedom. So, I can keep this as 1 and then accordingly get the other numbers normalized with respect to this one, which makes more sense. But in addition to that, this process is going to yield another very important and significant impact on the solution process. So, what we are doing here is the Rth mode shape is normalized by dividing in all the elements of this Rth mode shape by square root of the Rth mode generalized mass. Okay. So, 1 over square root of Mr is going to be the normalizing factor to get all the vector quantities normalized, and the reason why we do it is going to be shortly clear to you. Now, if you do that, it is almost like dividing this particular equation throughout by Mr. Okay. So, then square root of Mr gets distributed in this as well as this mode shape, right. So, now I can use the same equation in the normalized modal vectors, and the normalized modal vector is represented by a tilde on top of u. So, this is UR tilde transpose times mass matrix times UR tilde US tilde is going to be equal to 1, of course. Okay. Why it is 1? Because I have divided throughout by MR, and 1 square root of MR gets absorbed in the normalized modal vector here, and the other one gets absorbed here. This is going to be very interesting equation, right. Now, on the similar lines I can do it for the stiffness matrix. So, now if I use the mass normalized modal vectors, so R UR tilde transpose into K into US tilde will be how much? You recall that our equation was what? UR transpose K US was KR when R is equal to S, okay, and was equal to 0 when R was not equal to S. So, now if I divide this equation throughout by MR, which means if I divide it by MR on the left hand side and also divide this by MR on the right hand side, then this part is what I get here, because all these modal vectors are transformed to mass normalized modal vectors, which I define by or represent by tilde on U. And on the right hand side, what does this represent? It represents the rth natural squared natural frequency, PR. So, PR square is KR over MR, okay, and PR square is now the rth mode natural frequency, and that is how you get these equations. Okay. Now, coming back to this equation, what is our modal transformation that we defined? This was equal to individual modal vectors. Okay. So, U1 up to UN and was multiplied by the principal coordinates eta t, represented by eta t. It could be eta 1, eta 2, eta 3. So, this eta is the vector containing all the principal coordinates, eta 2, eta n t. This is we have this equation we have already discussed and shown how it works. Now, because these modal vectors are I mean if U1 is a modal vector, n times U1 is also a modal vector, right. So, I can use this this matrix as represented by U, and all of the elements of this matrix U are mass normalized modal vectors. Then this equation Q of t is represented by an equation like this, which is basically meaning that this modal matrix is basically containing all the mass normalized modal vectors. So, each one of them is like U tilde 1, U tilde 2 and so on up to all the n matrices. Okay, now what we do? We will now start looking at this equation and transform this equation into its into from the physical coordinate to modal coordinates or principal coordinates. So, this capital M stays as it is, but now Q I will replace. Now, the way I use Q double dot here, U is going to be your constant and eta being the time dependent harmonic functions. If I take the time derivative of eta t, I can represent that to be eta double dot t. So, now this m q double dot is now going to be replaced by eta double dot t and plus this k qt here is being replaced by so I am basically going to use this expression and its derivative to transform this equation in its these are given in the physical coordinates, you know, the degrees of freedom x1, y1, theta 1, all of these are being represented by the vector q. Okay, this is the actual physical response of the system to the coordinates which are the principal coordinates. So, they are not the physical coordinates, they are principal coordinates, and the equation of motion is now transformed into this equation of motion. Now, why are we all doing this? When you consider this equation, we know that all these equations are like in the form mx1 double dot plus k1 x minus k2 x2 and blah 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 equal to 0. There will be another equation in x2 where you will have minus k2 x2 plus k2 plus k3 into x3 and so on. The point is your governing equations of motion are all coupled equations. So, you have you know, all these n number of equations, they will all be coupled. That is why you saw the matrix K where having number of off diagonal elements which are basically indicative of the fact that the equations are all coupled together. So, solving such large number of equations, differential equations, for getting the solution when they are coupled is difficult, in the sense that it will take time. It takes time. It's the solution process is not straightforward. Okay. Let us now see how do we get around this problem of coupled governing equations of motion. So, now I am going to pre-multiply this equation that I have got by u transpose. Now, make a note that u is the modal matrix and I have simply pre-multiplied this . Now, what I get? U transpose means what? In this I will have your U1 transpose, is not it? The second row I will have the second row here U2 and so on, right, and I have your mass matrix here, and then I have U1, U2 and so on. So, if I consider the first modal vector multiplied by mass matrix and this, it actually turns out to be this U1 transpose mass matrix, the first element of this entire. So, this product U transpose M into U, it is all going to be all these columns are going to be like rows now. So, this is going to be U1 transpose going to get multiplied by the entire mass matrix, and this is going to be all U1, U2 and so on. So, if you really work yourself from here, the first diagonal element here, okay, this diagonal element is actually going to be U1 transpose M into U1. This off diagonal element is going to be U1 transpose M into U2. This second diagonal element is going to be U2 transpose M into U2. What is this value? Because we are considering this to be mass normalized modal matrix, the product of the same modal vector, with the mass matrix pre multiplication and post multiplication, this gives you a value equal to 1. This off diagonal element, what would it give? When R is not equal to S, okay, then you get the product to be 0. So, when you have two orthogonal vectors, modal vector 1 and modal vector 2, this orthogonality is now like a dot product of two vectors. When they are at 90 degrees, their dot product will be 0. Okay, if you are talking of two different vectors, independent vectors. Now, so U1 tilde or U1 transpose M multiplied by U2 is going to be 0, but if you use the same vectors, okay, same over the other, their product is not going to be 0. So, basically this is going to be 0, U1 transpose M U2 is going to be 0. In that sense, all other off diagonal elements where R is not equal to S, all those elements are going to be 0. And whenever you have the two vectors being identical or same, then the second diagonal element is going to be U2 transpose mass matrix times U2, and that is going to be equal to 1. So, you can think about it and work this out. You will realize that the entire product of U transpose mass times U is all going to be an identity matrix with all the diagonal elements being 1. So, this is going to be replaced as identity matrix, and how much will be this now? Likewise, if you work this out the way we have done for the mass matrix, it is quite straightforward to then represent here that you can show that if you use K matrix now, this is going to be what? Yeah, U tilde, that means mass normalized modal vector, when you multiply it with K, what do you get? PR square when R is equal to S, and is equal to 0 when R is not equal to S. You got that, right? Using this, when they are mass normalized, the product gives you PR square. So, what is going to happen is that you are going to get this as P1 square, the second diagonal element as P2 square, and up to Pn square. And all these off diagonal elements are going to be 0 because of the orthogonality. And that basically means that this matrix is going to be a diagonal matrix containing all the squared natural frequencies, which are basically your eigenvalues, times eta t equal to 0. That is basically is your transformed matrix equation representing this multi-degree of freedom system. The only thing is, instead of a physical coordinate like q, you are having this equation in terms of eta, the principal coordinate, the model coordinate. Now, do you see a difference between this equation and this equation? One of the major significant difference that you have between these two equations is that your first equation is a coupled governing equation of motion. Okay. This equation is a coupled set of coupled differential equations. But if you consider each one of the equations which is represented by this matrix equation, what you have, this I, the identity matrix, which means that you have 1 1 1 in the diagonal elements, all others 0, and eta 1 double dot t, eta 2 double dot t, and so on, plus the spectral matrix is nothing but what, p1 square, p2 square, all along the diagonal, right, multiplied by again eta 1 t, eta 2 t, up to eta n t equal to 0. Now, if you remove each of these equations, just take first row, what do you get? Eta 1 double dot t plus p1 square eta 1 t equal to 0. This is going to be your first equation if you take only the first row. The second row will give you what? Eta 2 double dot t plus p2 square eta 2 t equal to 0, and so on. So, what this transformation has done for you is that from an n coupled differential equations, you have got now n uncoupled equations of motion, and each of these equation is like a single degree of freedom governing equation of motion. Do you see that? X double dot plus omega n square x equal to 0. Okay. What is the advantage of these equations? You have standard solution available for this, right? But do you have standard solution available for such kind of a coupled multi-degree of freedom system? You do not. Think about multiple degrees of freedom means think about hundreds of them, right? But you have a standard format for all the 100 equations. You don't have to look further. I mean, this is all what we have already learned in the single degree of freedom analysis. So, in nutshell, now you should be able to connect all the dots. You have been wondering as to why we are doing all of this, right? Why we are writing this kind of equations where the orthogonality was discussed, why we are transforming to this kind of a transformation from physical to modal coordinates. All of that makes sense the moment you get to see the final result here, which shows all your coupled differential equations of n number of such equations. Suddenly you see that they are all getting converted into n single degree of freedom system equations of motion, which are quite similar to a single degree of freedom system. In fact, each one of them represents the motion that is taking place in that particular modal coordinate eta 1. The moment you write the solution eta 1, eta 2, eta 3, which you know now how to get, you can plug it back into this transformation, right. So, once you solve it for eta, you basically know this vector completely. You already know this modal matrix, because what is modal matrix? It is ultimately coming out of the eigenvalue analysis. So, this is something which is known for your system, right. The moment you do that, you get the physical response, because you are not interested in getting the response in principal coordinates. You are interested in knowing how much is the motion of the physical system, that is x and y and theta, right. So, the objective now, or the next step now for us, having shown that the power of the modal transformation and the orthogonality property is to decouple all these governing equations of motion. so that you get a set of ordinary differential equation in only one coordinate, decoupling it with all the others, you can solve it and then plug it back through the same transformation to get the physical response. Okay. So, that is the power of this transformation that we discussed. Okay. Essentially, the whole purpose was to decouple all your governing equations of motion. Once you decouple it, your standard expressions for a single degree of freedom system will simply suffice, and that is what we shall discuss, how to make use of what we learned for a single degree of freedom system to solve this multi degree of freedom system. And I hope now you are able to realize and the importance of studying the single degree of freedom system. Multi degree of freedom system is something which there is nothing great in it, because all what you learned, all the basics of the first single degree of freedom system will now get implemented for arriving at the solutions. Summary of this lecture: we discussed the orthogonality property of eigenvectors, in which the eigenvectors, how they are orthogonal with respect to stiffness and mass matrices was discussed. In addition, we got introduced to the solution approach, understood how the coupled governing equations of motion actually get decoupled by using the modal matrix and the orthogonality property, which actually is the foundation for an efficient calculation of finding out the response of a multi degree of freedom system. These are the review questions that you can attempt, and these are the answers.